Hi there, this is Shazad. Welcome to my channel Physics of Characterization Technique. So chiefly here I will talk about the spatial resolution of the secondary electrons in a scanning electron microscope. But before starting this, let's take a quick review. So what we have learned till now, here we can see when the when the incident beam strike the sample surface or the specimen, we have we have different signals generated from the sample surface, like this SE1, SE2, SE3, SE4, and this BSE. So chiefly here I will talk about the secondary electron, which will be detected by the SEM detector, the ET detector, uh, Everhard Thorne detector. So as we know, we have different signals generated from the samples. So here let's talk about the this SE1. So SE1 are generated by the direct interaction with the incident, this primary beam, electron beam, and therefore carries the highest spatial resolution information, because the spatial information is chiefly determined by the size of the primary electron beam. So the spatial resolution of the detection of this SE2 SE2 electrons. So the spatial resolution of this SE2 is poorer because this SE2 are induced by various scattering or the multiple scattering or collision of the electron inside this specimen. Here you can see with this red color, there are so many scattering of the electrons. So these SE2 are the part of this multiple scattering of the electron. So this SE2 will make the image poorer. So because it will provide a poor spatial resolution. So this spatial resolution is mainly determined by this this range, which is designated by this d distance. All right. So here, one more thing I want to discuss here. In secondary electron microscope, the spherical aberration of the probe forming lens is increased with the increase of working distance, which results in large electron probe size. So let me introduce a couple of terms over here. Yes. So what is working distance here? The This is the working distance. Working distance. So working distance is the distance between the aperture, this aperture, and the specimen surface. All right. See what. Let's talk about the spherical aberration. So here in this image, you can see this is a lens and this is a light which is coming and strikes the lens. So all the light converge at a particular point. This is called the focal point. But here in this image, just wait. Uh, here in this image, you can see uh, we have the light is deviated from its path or the way. So there is no particular focal point. There are many different particular focal point. So this condition is known as the spherical aberration. So this situation happens in case of this SEM. Okay, so so I've already told you the if the spherical aberration of the probe forming lens is increased, the with the increase of working distance here, when this spherical aberration, sorry, when this working distance increases, this spherical aberration will increase. So we need to avoid this condition to happen. Okay, so here you can see that the how we can resolve this situation. So the need to have better spatial resolution of SEM leads to shorten the working distance and consequently to change the SEM detector position. So we can reduce this working distance, and of course we can maintain the distance of this detector. So here it is clear that the interaction volume is larger when the semi-convergence uh, angle of the SEM probe is larger. Here you can see this is the semi-convergence angle, and this is our the incident probe, and this is the optical axis. The electronic beam is coming from the just right from the aperture, and we just strike the specimen. All right, so here you can see this is if the if this distance is larger, that means we have this alpha larger. So we don't want this alpha to be large. We don't want this condition. No. If we increase this further, we will spherical aberration, and that will affect the image. So we don't want this condition. No. Okay. So how can we resolve this situation to happen? So avoid using too large probe forming aperture uh, to minimize the interaction volume. So the entire motive is to reduce the interaction volume. The interaction volume means when the light will come and strike the sample, uh, the interaction volume will, if the interaction volume is larger, suppose if the interaction volume is like this, so we need to avoid this condition. Why we want to avoid this condition? Because if the interaction volume is larger, we will have different signals like the X-ray, the continuous X-ray, uh, and the Auger electron, the backscatter electron. But we don't want these radiations for the time being. We just want the secondary electron. So we don't want interaction volume to be very large. It should be very small if we want to if we want the secondary electron image. So just avoid this condition to happen. So avoid the use of too thick specimen to minimize the interaction volume. So here the sample thickness must be smaller to minimize the interaction volume. And also if the sample thickness is too thin, there will be a problem that will give us a poor image of the SEM. So avoid this condition to happen. It should not be, the specimen thickness should not be too high, too high or too thin, too thick or too thin. Okay. The third point is avoid the use of too small probe, forming aperture to minimize the aperture effect on the spatial resolution. So we should avoid this condition to happen so that we can get the better secondary electron image. All right. So this is all about the uh, spatial resolution of secondary electron, uh, which the situation happened when the incident light strike the sample, and we have different kind of signals generated. Okay, I hope you found this video useful, and I hope that you will share this video with your friends. So if you liked it, make sure you press like, press subscribe, and hit the notification button so that you get notified when we have new videos released on this channel. Thanks for watching this video, and I will see you in the next one. Bye bye.